Hello, I think you are Professor Kejing, right? Kejing Wang.
Yes.
Thank you, Kejing. So it's my pleasure to talk at the ACI Spring Convention. This work I will talk about is joint work between my team in Southeast University and the team from Hosium Innovation Center in France. I will talk about the effect of drying environment on mechanical properties, internal relative humidity, and pore structure of 3D printed concrete. Okay.
Yeah, we can see that very well. So go ahead.
Okay, great. Thank you. I will continue. Okay. When we talk about 3D printing technology, we know there are many advantages like no formwork. It's very flexible in design, labor saving. Yeah, many advantages. But one issue about 3D printing concrete is it works with no formwork. This will cause some problems. That means after concrete is printed, right after printed, the concrete is in fact directly exposed to the environment. That means there is no protection from the formwork as traditional concrete. So this will cause some other problem, like very early shrinkage will happen on the surface due to the evaporation from the surface. Okay, and another issue about 3D printing concrete is the mixture we normally used. We have done a statistic about the mixture of normally used 3D printing concrete. We found that most of the concrete used are mortars without any aggregate. Of course, this technology is developing very quickly, so we know there are some published papers about the use of coarse aggregate now, but early works, we mainly use mortars. So this means in 1 cubic meter of concrete, we need to use about cementing material about 800 something. That means the binding material for 3D printing concrete is about twice of conventional concrete. So this is not low carbon, okay? And because of the lack of coarse aggregate, we have some problems about the hardened concrete. For example, this is reported by Professor Scooter's group. The dry plastic shrinkage is very severe. We also checked the quality. I mean, the shrinkage after the printed elements are exposed to the environment very long. After long exposure in the air, we also find some cracks. Okay, these elements are printed with mortar, not without any coarse aggregate. So my talk today is about the dry shrinkage of 3D printed mortar, just to understand how the drying will affect the mechanical strength development, and if the anisotropy characteristic is influenced by drying curing, and how about the pore structure difference between cast and printed concrete and under drying condition, and how the internal relative humidity influence the pore structure and then the mechanical strength. Here is a mixture we used for 3D printing. We use cement, silica film, sand. The maximum diameter for sand is 1.18 millimeter. And we also use some PCE and HPMC to modify the rheological properties for printing. And here are some basic properties about the printable concrete. The setting time, final setting time is very long. That means we can have a relatively long time to print. And we use a very simple test method to estimate the buildability. Use a column, then we test the slump height, okay? And we use the slump table test to test the flow. Here we the static yield stress with development with time. We can see the static yield stress develop is still within the scope for printing within 30 minutes. Okay, here is the printer we used. It's a Gantry 3D printer. Here are the elements we printed in the factory. You can see we printed in two different ways. The element printed with the pass A. Here this is for the test of shrinkage along the printing direction. For the element printed with pass B, this is for the test of the shrinkage with some more interfaces between horizontal filaments. Okay, and here are the curing conditions. We mainly consider three different curing conditions. S represents the standard curing with very high relative humidity, above 95%, and dry D stand for the curing condition with a relatively lower relative humidity at about 60%. And for the condition of dry and wind, that means we use both dry at a low relative humidity and use some fan to impose some wind on the surface of the printed elements. Right after printing, we use a chamber. We call this environmental chamber to cover the surface of the printed elements. Okay, here is the setup about the chamber. Inside the chamber, we can see we put the fans here. Then we can see the 3D printed elements. Okay. We tested the mechanical properties, like the flexural strength from three different loading directions, and the compressive strength and the split tensile strength. We split on the surface of the matrix and two different interfaces. Okay, here are some results. Okay, here is the compressive strength and the flexural strength. In the two tables, we compared the strength we obtained after curing under dry and under wind. We compared the strength. Here is the compressive strength. You can see that under drying conditions, here we can compare the strength at different curing times. Okay, for the printed loaded at X direction and at Y direction, that means we got the mechanical properties from different directions. You can see that the strength decrease when we compare with the standard cured. That means we cured at a very high relative humidity. We can see when we load at different directions, the mechanical strengths are dropped sharply when we compared with the specimens cured under high relative humidity. Here we can compare the dry condition and dry and wind condition. You can see when wind is applied to the samples, the mechanical strength drop is much higher, a little even higher than under the dry dry condition. And another result is we can see when compared with the cast concrete, okay, the drop of the mechanical strength is normally higher than the cast concrete. Okay, here is the result of the flexural strength. Okay, very similar results can be obtained. Similar to the compressive strength, but at higher, at later ages, and maybe at 28 days, the drop when compared with the cast concrete, the drop of flexural strength under different curing conditions becomes lower. This is because the concrete are getting stronger and stronger at the later ages. Okay, and we also calculate the anisotropic index. We all know that because of the layer by layer deposition process, 3D printed concrete is anisotropic. Okay, so we use this formula to calculate the anisotropy index of compressive strength and the flexural strength. This is interesting that we found that, for compressive strength, the index, the anisotropy index we calculate is is very low when compared with that for flexural strength. You can see here for flexural strength, the index is very high. Okay, and when we compare the anisotropic index at different curing ages, we can see that normally at early ages we've got a higher anisotropic index, and but the curing condition, whether it's drying condition or drying condition with wind, okay, we can see that the anisotropic index doesn't seem to change a lot. That means the curing condition did not change the anisotropic property of 3D printed concrete. Okay, that is because the anisotropic property is mainly caused by the existence of interfaces. But the interface, in fact, is not very much affected by curing conditions. Okay, here are the results about the splitting tensile strength. Okay, we did the splitting from different directions, from mainly two interfaces, and one from the at the matrix. We can see here the results. Okay, no matter which direction we did the split tensile test, you can see there is no big difference. In fact, there is no difference between the splitting tensile strength, whether the 3D printed concrete is cured under dry and wind conditions. Here you can see very similar results. And of course, at 28 days, that splitting tensile strength is much higher. Okay, this means this result is quite different from that of flexural strength. This is also because the splitting tensile strength is not very much affected by the interface. Okay, and here are some results about the internal relative humidity development inside the concrete. We test the relative humidity evolvement at different depths of the 3D printed concrete. Here we can see that for 3D printed concrete at the same depths, the relative humidity drops much quicker than the than cast concrete. Okay, it's also very interesting to find that at early ages, you can see here as three figures. You can see the relationship between the compressive strength and the internal relative humidity. When we compare their relation at the same curing age, we find that at early ages, okay, this relationship is very dependent on the age. At very early ages, we can see, the slope of the relation is much higher and is much scattered. But at 28 days, it's much slower, like this one, the 0.68. That means early age curing is very important for 3D printed concrete, and the mechanical strength is very sensitive to the early age curing. So because of the lack of formwork, the protection of formwork at very early ages, the mechanical strength is indeed very much affected by the curing condition. Because this will affect the internal relative humidity. And we used X-ray CT to reconstruct the structure, and we extracted different parts to check the pore distribution of 3D printed concrete and compared with the cast concrete. Here are some results. Here we can see for the printed concrete, we can see some connected pores at the interface. But for cast concrete, of course, we can also see some air entrapped voids, but the distribution is quite different. We calculate the pore distribution at different pore size. Here you can see for 3D printed concrete here, we've got much more pores having the range between 0.1 to 0.4 millimeter. But for cast concrete, the number is much lower. And for printed concrete here, we've got also some large pores, like here 2.2 to 2.4 millimeter. Okay, and we calculated the pore connection. Yes, here you can see for the printed specimens, the maximum connected length in the printed concrete is about 0.61 millimeter. But for cast concrete, this value is only 0.34 millimeter. That means for 3D printed concrete, the pores are more connected than cast concrete. Okay, here we also compared the dry plus wind, its effect on the pore distribution. For drying condition, we've got many pores between this range 0.1 to 0.4. But when wind is also imposed on the surface to further accelerate the evaporation of water, we can see here we've got more pores in this range here, much more pores in this range, and we also calculate the porosity of different samples, 3D printed and cast concrete, from the top surface until the bottom, and we calculate the top filament, the top interface, and the bottom interface and the bottom filament. Here we can see the result about the porosity, and TF means top filament, and BF means the bottom filament. So we can see that on the top of the specimen, we've got much higher porosity than the bottom, and between the surface and the bottom, we can see for the interlayer, their porosity is lying between the top surface and the bottom. But when under different curing conditions, we can see under dry condition, the porosity lies between the saturated situation and the dry and the wind. That means dry and wind, under this situation, we've got the highest porosity, okay? And because for mortar, the shrinkage problem is already a problem if we want to use 3D printed concrete in practical engineering. So we have to develop some concrete with coarse aggregate. Here are the 3D print concrete with coarse aggregate developed in my lab. You can see a very good bonding between filaments printed. Okay, there is no very obvious interface or voids between interfaces. Okay, and we also developed some 3D printed concrete with PP fiber incorporation. You can see here PP fiber incorporation can very effectively reduce the total shrinkage. And very interesting is we find that on the 3D printing, the distribution of the PP fibers quite different. Okay, the PP fibers are more orientated along the printing directions. But for cast concrete, you can see the three-dimensional distribution of these fibers. Okay, this is the last slide. Okay, we've got some application of 3D printed concrete in Nanjing and in other cities in China by my group, because I'm working together with the industry to develop the 3D printing technology. Okay, yeah. Okay, then the conclusion. The 3D printed concrete is more sensitive to curing conditions. Okay, compressive and flexural strength is significantly affected by curing condition, but the splitting tensile stress is slightly influenced. The mechanical properties at specific edges are linearly correlated to its internal relative humidity. And the anisotropy of 3DPC is not much affected by severe curing conditions. The pore shape of the printed sample tends to be elongated and connected after extrusion. This work has been published. Okay, and this work jointly supported by Hossein and by the National Natural Science Foundation of China. And yeah, we co-supervise my PhD student Malay with Hossein Group, or with a team from Hossein Group. That's my presentation. Thank you.